What's up, everybody? Welcome back to my channel. We have some really special content for you today. Let's first check in on our sponsors. Totally joking. I'm laughing that distance learning 2020-2021 has made me into a YouTube star. All 11 of my subscribers, I'm sure, would agree. All right, let's jump into it. What are we doing today? We're doing organic mechanisms, reviewing what you need to know from 20.1 in HLIB chemistry. So I'm going to go through the mechanisms that you need to know: nucleophilic substitution, SN1, SN2, and electrophilic addition. We did these between May 7th and May 28th, those two high-level sessions. These are the ones that you need to know for your for the 2021 school year. Electrophilic substitution and reduction, I'm going to talk about these as well. I mentioned this in class. Some of you told me you want to be able to close the book on organic mechanisms, know everything you need to know. So feel free to watch these this year. Otherwise, you'll just watch them next year and learn them next year, ideally both. But I am only testing you in the final through electrophilic addition mechanisms. Of course, electrophilic substitution, you do need to know the reactants, products, and conditions because that was in SL. But the actual mechanism is in HL, and we'll do it in August, I suppose. All right, let's jump into it. Nucleophilic substitution. There's two mechanisms we learned, SN2 and SN1. We should be able to draw those mechanisms, and then we'll go through the other information we need to know. So with both nucleophilic substitutions that we did, there was a particular nucleophile that we used. The IB tends to show nucleophilic substitution with the nucleophile OH-. What makes OH- a nucleophile? The fact that it has lone pairs. It has a negative charge, so it's a really good nucleophile. It's better than something like water, for example, because it does have a full negative charge. We tend to use NaOH to get that OH-. You could use something else, but let's just use what they usually give us. This would be my other reactant. So let's go ahead and draw this. Bromoethane. So bromoethane, I have two carbons, F, bromo, and then I'm going to show the hydrogens. Notice I always start the the SN2 mechanism in this way, showing my molecule in this way, leaving space for a backside attack coming in on the opposite side of the bromine or of whatever halogen you have. So my first thing that I need to show is that backside attack. So I'm showing my nucleophile. I'm showing the lone pairs because it's always a good idea. If you don't show them, you don't lose credit, but I like to be in the habit of showing the lone pairs, and I'm showing the curly arrow, which always moves from the lone pairs to whatever it's attacking, to the thing it's going to bond to. So my nucleophile attacks that carbon there. I then get a transition state. So what I'm about to show, it's not an intermediate. It never exists as its own molecule that you could isolate. It is just an unstable transition state. This is what we theorize it to look like as the change is happening. So the hydroxide is in the process of forming a bond to carbon. Bromine is in the process of leaving. You can show the bromine leaving in the first part of the diagram or the second part. I tend to show it in the first part just because that's how it is in Cognity and in the IB material. So we'll show it like this. My transition state, very importantly, in order to get full credit, the transition state does have a -1 charge, so you need to show that. And I show the CH3, and I'm missing a hydrogen here, so I'm going to show all the substituents. We get this nice little 5-pronged thing. We know carbon's not happy making 5 bonds. Let's fix that. Let's show the products that form, and very, very quickly, because it was just a transition state. Hydrogen, CH3, hydrogen, and I'm just kind of showing this in a weird way in terms of stereochemistry because I'm showing basically what we had here without the bromine. Of course, carbon is tetrahedral. So if I were to show the correct stereochemistry, this molecule would end up as tetrahedral, unsurprisingly. And let's, oops, I drew this a little too far over. Hydrogen, OH, hydrogen, CH2, CH3, OH, ethanol, plus bromine. All right, let's look at an SN1 mechanism and how it's a little bit different. So SN1, it's going to use that same nucleophile from NaOH, which will give us Na plus and OH minus. OH minus, of course, will be the nucleophile. It has a negative charge, and really what makes it a nucleophile is that it has lone pairs. So let's do it. 2-bromo-2-methylpropane. Notice this is going to be tertiary. That's good. SN1 likes tertiary. So here we go. 2-methyl. All right, so 2-bromo-2-methylpropane. I still have the same exact nucleophile coming in to attack, but before we do that, this one actually starts out a little bit differently. My first step here is for the bromine to leave. So up here, the bromine left kind of at the end. We saw the bromine leaving after the nucleophile had attacked. Here, the bromine leaves first. So let's try that again. The bromine leaves first. This time I get an intermediate. So it is actually an intermediate. There's a two-step process here. This one does not refer to the number of steps. It refers to how many reactants determine the rate. So this is a two-step process. We have an actual intermediate. It's not very stable, but it is an intermediate. So I'm going to get CH3C, CH3, H3C, Br minus, and excuse me, that Br is already gone. I have a carbocation here. Carbon is positive when positivity is a bad thing. Carbon does not like being positive. It needs a lot of help if it's going to try to be positive. It gets some help from being tertiary. These other carbons help distribute that positive charge. That's a positive inductive effect. This intermediate is also why I have a polar protic solvent, because I choose a solvent that can interact with, form cohesion with, form IMF with that positive charge there to help stabilize it. So carbon really doesn't like being positive. It needs lots of help if it's going to be positive. It needs that positive inductive effect from being tertiary by having these other carbons attached and sharing the positive charge. The polar protic solvent helps stabilize that charge. It's super, super positive, so it's really happy if a nucleophile comes along that positive wants to attract something that's negative. OH minus is there, luckily, saves the day. Notice I'm drawing my arrows again from the lone pairs to where it's going to bond. Those do need to be drawn exactly like I have it here. And then, of course, we have our final step. Carbon, OH, CH3, CH3, plus, remember we still have that Br minus from when it left back here. All right, to summarize, what did we talk about with SN1 and SN2? Well, the rate of reaction is dependent on primary, secondary, tertiary, so SN2 works really well with primary, SN1 works really well with tertiary, again, because of the positive inductive effect. Both have some unstable thing that happens in the middle of the mechanism. For SN2, that's a transition state. For SN1, that's actually a full intermediate. There's two steps to SN1. SN2 tends to use polar aprotic solvents. That's to avoid the OH minus nucleophile interacting with anything else. It's to keep OH minus free in order to react. That's still a problem in SN1 because you're still using OH minus, But the benefit of using a polar protic solvent outweighs this disadvantage with the OH minus. We really need a polar protic solvent because it stabilizes the carbocation. Carbon is super needy. It really, really doesn't like being positive. We need the positive inductive effect. We need a protic solvent. Um, Even though a protic solvent will have the issue of maybe blocking some of the nucleophile ions from attacking it, because of course a polar protic solvent will interact with the OH minuses that are trying to do their attack. The benefit of stabilizing the carbocation outweighs any negative interactions or any downsides of being able to interact with OH minus. In SN2, we don't need to deal with stabilizing anything, so we just maximize efficiency as much as possible and avoid any interactions with OH minus. And then this last point was just something I told you. SN2 begins with a single enantiomer, ends with a single enantiomer. So, of course, that product would be optically active if I just have one enantiomer. SN1 begins with a single enantiomer, ends with a racemic mixture, which is a 50-50 mixture of both enantiomers. If I have a racemic mixture, that's actually optically inactive. Why? Because half of the molecules are spinning light one way, half are spinning it the other, and it ends up being optically inactive. It's not going to rotate light in one way or another as a whole sample. I just wanted to go through this practice question because we did it briefly in class, and I think it was a little bit confusing because this I here kind of looked like Cl. So let's go through this. So here I have CH3Cl. Here I have the same molecule, but instead of, sorry, yeah, oh, whoops, that was right, Cl. I have the same molecule, but I have I. This thing kind of looks like Cl, but it's not. It's Ci, which I know because Cl wouldn't form the right number of bonds. In C, I have CH3. I'll just draw a skeletal formula here. 1, 2, 3, 4. 1, 2, 3, 4, Cl. All right, so I have tertiary with Cl as a leaving group, Cl minus, tertiary with I minus as a leaving group, primary with Cl minus as a leaving group, primary with I minus as a leaving group. We talked about on May 7th, slide, let me get you the slide number. Oh, what slide am I on? Very strange. Slide 30. So May 7th, slide 30 from the HL topic. That's where we talked about rate of reaction. Both the position of the halogen and the leaving group can influence rate. That's what this is getting at with rapid. All right, so the first thing I need to notice is that I have aqueous hydroxide ions. What's my solvent if I'm aqueous? H2O is my solvent. That is polar protic. H2O breaks up into H plus and OH minus. It is indeed protic. All right, so water is my solvent. Cool, polar protic. That's really good. With SN1, SN1 works really well with tertiary. So I can cross off C and D. Now I need to figure out which is a better leaving group, Cl or I. Well, the C-Cl bond is actually stronger than the Ci bond, which I can figure out based on bond enthalpies. I can look up the bond enthalpies for these different bonds. So because Ci is a weaker bond, it makes a better leaving group. Right? The bond isn't being held as strongly, so I leaves more easily. It's not being as it's not being attracted as tightly because I is bigger. So I is a really good leaving group. And so B is the answer. All right. Next mechanism, electrophilic addition reactions. So electrophilic addition reactions, we studied these in general. Unsaturated alkenes, something gets added across the double bond to become saturated. Let's look at the mechanism. We're going to look at the mechanism for halogenation and with a halogen and with a halide. All right, so starting off nice and simple, halogenation with a halogen. So let's look at what this mechanism looks like. Hydrogen, hydrogen. I know that does not look like an H. Let me fix that. All right, and now I have Br2. So Br. What's going to happen here? It's close to my double bond. My double bond has a high kind of proportion of, I don't know if proportion is really the word I want there, but high proportion of negative charge, a high density really is the word that I want, a high density of negative charge. That's going to induce a dipole in my BR. So I'll get an induced dipole here. There's a good gizmo in that, and that's linked in the presentation. So I'll have a partially positive one BR atom, partially negative the other BR atom. Let's see what would happen. My arrow, again, always starts from the lone pair, starts from the electron. So it's going to start from where I have lots of electrons in the double bond. Essentially, the double bond is going to attack, oops, I really do want this to be a curly arrow, the bromine, and then the other bromine can leave. All right, so you're going to want to be careful here to draw this correctly. I now have a bromine attached. People tend to not want to use 90-degree angles here. Your work's going to be really messy if you don't. So show these 90-degree angles. Show that this bromine here just formed a new bond to the molecule. I have another carbocation because we've only attached one carbon at this point. All right, and then remember, this bromine just left. Bromine is negative. We have a carbocation. So again, feel free to draw in lone pairs here. That's totally great. From the bromine, which has lone pairs, is now basically kind of acting as a nucleophile. This is really electrophilic substitution because my electrophile is right here, my positive thing. But now bromine is negative. Bromine is able to attack that carbocation in the second step, and then we get our beautiful product. 1,2-dibromoethane, colorless. We use this in the test for saturation, which you saw in a lab. All right. The same thing happens if I have a halide. I'm going to draw, whoops, I got ahead of myself, sorry. Carbon, hydrogen, hydrogen. My halide, this time I don't need to worry about an induced dipole because I have a permanent dipole because of differences in electronegativities. And so from the double bond to the partially positive hydrogen, from the single bond to the bromine, just like before. And now I'm drawing this with 90-degree angles. Very intentionally, that hydrogen just got added. I don't want to draw another arrow because that's confusing. This hydrogen is the same as this hydrogen. Carbon, carbocation, bromine is then available to do an attack. And we get our product. All right. So this gets a little bit more complicated if I have an asymmetric alkene. This happens with halides and asymmetric alkenes. So I'm going to draw an asymmetric alkene like propene and that same halide as before. So now what happens? The same thing we just saw, the same exact mechanism. The double bond attacks the partially positive thing. The partially negative thing can leave. But now we need to be careful. There's two things that could happen. I could have hydrogen. So I'm tracking this hydrogen. Hydrogen could join here, CH3, and this already had a hydrogen. Or I could get that same thing, but hydrogen joining on the other side of the double bond. So let's see what that would look like. So that same exact thing, but hydrogen going on the other side of the double bond, and this guy becoming positive. Hydrogen tends to go where there's already more hydrogens. So the hydrogens that were already on this molecule were two hydrogens on the first atom and only one hydrogen on the second atom. So the hydrogen right here from the HBr, it's going to want to join with on the carbon that already has more hydrogens on it. And this is Markovnikov's rule. I know I'm saying that wrong. I'm so sorry. I struggled with it in class too. I know you're all sitting there correcting me. It's okay. So this hydrogen is joining on carbon 1. It prefers carbon 1 because carbon 1 already had two hydrogens on it, whereas carbon 2 had a single hydrogen. So again, both of these will happen, and then Br minus will attack. Br minus will attack. Whoops, I drew that. I want to attack from way over there. Br minus will attack. We'll get our two products. And notice I have 3 carbons, so I could get a bromine in the middle on the second carbon. And that's it. Yep. Or let's go ahead and copy and paste. Or the bromine flip-flopped. This wasn't an issue before because we just had ethene. So if a bromine got added here or here, we end up with the same molecule, right? This is going to be carbon 1 because it has a bromine on it. Whereas here, I now have carbon 1, 2, and 3. Bromine is on carbon 2, or carbon 1, 2, and 3 with bromine on carbon 1. According to Mark's rule, this will be the major product. This will be the minor product. And this only happens if you have an asymmetric alkene, which just means you have an alkene. This is asymmetric because on one side there's a methyl group attached and not on the other. So just like we said, the hydrogen is going to prefer going to where there's more hydrogens. So the hydrogen preferred going to where there is more hydrogen, making this product the major product. Both will happen. You'll just get more of the major product. All right. Electrophilic substitution. Now this is beyond what we did in HL time, but you'll have to know it eventually, so probably worth your time to watch. The electrophilic substitution reaction we studied was with benzene, of course, with an electrophile getting attacked from the high electron density coming from those delocalized electrons on benzene. So what happens is the high electron density attacks some electrophile. This is just a really general mechanism. And then this hydrogen that was here on the benzene, this is actually going to attack because there's going to be a slightly negative charge and it's going to be able to leave. So benzene, that was the electrophilic reaction we studied. We saw several examples of this in SL time. This is taken directly from your All Organic Reactions Mechanisms document. We saw with nitrogen, we saw with chlorine, bromination, chlorination, nitration, all these different options. So let's look specifically at the nitration of benzene, what that mechanism would look like. So step one, the high electron density attacks from the benzene ring to my electrophile, which in the case of nitration was NO2 minus. I then make this hydrogen explicit. This hydrogen, the electrons from the carbon-hydrogen bond here are going to go back into the benzene ring, essentially, because the benzene ring lost electrons to form a bond here. We didn't lose, but the electrons went ahead and attacked the electrophile. And so it's going to be a little bit electron deficient. Benzene doesn't like that. It's going to pull those electrons from the carbon-hydrogen bond to that same carbon that the nitrate just got attached to. And then the H plus is able to leave. And we end up with our nitrobenzene. All right, so that is all you need to know in this mechanism. You should be able to reproduce this. I don't expect this to come up a ton, but it could, so showing it to you. Reduction reactions. We studied oxidation reactions in SL time. We studied primary alcohols oxidizing to aldehydes, primary alcohols oxidizing to carboxylic acids, depending on if you just did reflux or if you did distillation. Secondary alcohols oxidizing to ketones, tertiary alcohols not oxidizing. Turns out this can go in the reverse. And these things, the aldehydes, carboxylic acids, and ketones, can be reduced, which is the opposite of oxidation. The nice thing here is you only need to know these conditions. This is not another mechanism. You just need to know the conditions, which is the reducing agents. So remember, primary alcohol can go to aldehyde. If an aldehyde goes back to primary alcohol, these are the conditions you need. NaBH4, that was bigger than I thought. NaBH4 and H plus aqueous acidic conditions. If a ketone gets reduced to a secondary alcohol, that's the reverse of this reaction. The conditions are the same, NaBH4 and H plus. The only other reduction that we have in the syllabus is reducing nitrobenzene. So that's undoing the reaction we just saw here, doing reduction. And those conditions are tin and concentrated HCl to go from the nitrobenzene back to the benzene with NH3. So this would be kind of a weird reaction. I don't know, but it could come up. So these are conditions you need to know. All right, there it is. Take a moment, pause, say something nice to yourself. You've worked hard. Organic chemistry is hard, but I'm proud of you. You're in it, you're doing great. Let me know what questions you have, as always.